In this experiment, we are going to use calorimetry to determine the specific heat and the heat of a solution. Let's do the specific heat first. The basic idea is we'll take a metal, heat it up, put it in some water, and see how much hotter it gets. A higher specific heat metal should warm the water more if it had the same number of grams and the water was the same amount in each case. So imagine this sort of test question to gain an understanding of this experiment. We take 100 grams of a metal pellet that we have heated to 95 degrees Celsius. We can do that by putting it in hot water. We then transfer it into 100 grams of room temperature water, and we find that it warms up to 29.4 degrees Celsius. What would be the specific heat of the metal pellets? Well, here's the basic idea of how you're going to do that. Well, we'll find how much heat the water absorbed when we put the hot metal in it using Q equals mc delta T. Notice all those W subscripts. That's to help keep track of when you're dealing with water and we're dealing with metal. So specifically, this is the heat that the water absorbed. It's equal to the mass of the water times the specific heat of water, which is that number right there, times the change in temperature of the water. And it looks like it went up by about 4.4 degrees. All right, so fine. That'll tell us how much how much heat the water absorbed. Now, where did that heat come from? It could only have come from one place, assuming we have good insulation, and that is from the hot metal. And therefore, the heat that was absorbed by the water must have been lost by the metal. We can now find the specific heat of the metal since we have enough information to solve it. In other words, once again, Q equals mc delta T, but here now it's all metals. And we do have this number, see? It was the number that you calculated before. So now the only unknown here would be the specific heat of the metal. So simply rearrange and solve for that, and you should find the specific heat of the metal in joules per gram degrees Celsius. Look it up in a table, and you should be able to identify your unknown metal. A couple of notes for this specific experiment. Sign out the calorimeters. Be sure to clearly identify your unknown. Start collecting data using the computers before you add anything to the calorimeters. It's okay if it runs for a little bit and then you add your metal. Don't forget to manually stir. These calorimeters can do that, and I'll show you how. The calculations, let's find the change in temperature for parts 1 and 2. Let's find the heat that the water absorbed, and let's find the specific heat of your metal. So those are the three calculations we're looking for. Part 2, heat a solution. Very similar to the last experiment, but in this case we're going to add a salt to water and it should cool the solution. And we can find the heat of solution doing that. Fairly straightforward. Here's a sample test question. You take 100 grams of ammonium nitrate, and that is in fact the salt we'll be using. We place it in 100 grams of water that is at 25 degrees Celsius, and we find that it cools it to 18 degrees Celsius. Calculate the change in enthalpy of the solution. Well, here's how we do it. We find the heat released from the solution using Q equals mc delta T. Notice all the S subscripts. So it's always for the solution. With one exception here, we're going to assume that this solution is largely water, and water is the highest specific heat anyhow. And so we're going to use 4.184 for that number. Plug in your data and solve for the heat of the solution. That should give you the number of joules for however many grams you used. And then do 2 unit conversions, joules to kilojoules and grams to moles, to give the answer in kilojoules per mole. A couple notes. Start collecting the data before you add the salt, just like we did there. And beware of the supercooling region. So when things cool down, they can kind of overcool and then stabilize. So you want to ignore that little trough, if you will, and just go with the baseline numbers. And you're always graded on precision, so be sure to do that. There are 5 calculations for part 2. The heat of solution, which is right here. The moles of ammonium nitrate that you use, convert from grams. The heat of solution for each trial. And then the average heat of solution when you average the trials. Also, please calculate the theoretical heat of solution using standard values. Here's your chemical reaction. It's really just dissociation. And remember that the heat of solution theoretically would be the sum of the standard heats of formation of your products, there's 2 of them, minus your reactants, there's 1 of them. Look them up in a table and get an answer. It'd be interesting to see how that compares to the calculated value, the experimentally determined value. Okay, that's all for today. This is using calorimetry to determine the specific heat and the heat of solution.